Hi, this is section 8.4, mathematical induction. So mathematical induction is a process used to prove that statements are true for every positive integer n. So for example, if you're trying to show that this statement is true for all n, then you need to use mathematical induction. So the first step is to show that p sub 1 is true. That means when n is equal to 1. And then you assume that it's true for any arbitrary k. So you assume that pk is true. And then our job is to show that the next term is true. We need to show that p sub k plus 1 is true. So if you show that those two things are true, then we can conclude that it's true for every positive integer n. So let's start. So our first step here is to let p sub n be the statement, and then you just rewrite the statement itself. So you just write exactly the way you see it, and that's always the first step. So that's our statement, p sub n. Now we need to show that p sub 1 is true. p1 is true since, for p sub 1, that's just the first term. If p sub 2 would be the first two, p sub 3 would be the first three, so on and so on. So we're showing that just p sub 1 is true, therefore we're just looking at the first term. 1 is equal to, on the right side, you substitute 1 in for n. So if you do that, you're going to get 1 times 1 plus 1 over 2. That's 1 equals 1 times 2 over 2. And clearly that is 1 equals 1. So that means that p sub 1 is true. All right, now the next step in the process is to assume. So assume that p sub a is true. All right, so that means that we're assuming that the statement is true for some arbitrary k. So we're going to write 1 plus 1 plus 2 plus 3 plus ... plus k is equal to k plus 1 over 2. So we're assuming that this statement is true. All I did was replace the n with a k on both sides of the equation. That's all we did. So we're assuming that this is true. That's called the inductive hypothesis. Now we must show that p sub k plus 1 is true. So let's write out p sub k plus 1. Well, p sub k plus 1 is 1 plus 2 plus 3 plus ... plus k, plus the next one after k is k plus 1. So what is that equal to? Well, let's see. We need to show that that is equal to the right side. So what you do on the right side is you replace the n's with k plus 1's. So that would be k plus 1 times k plus 1 plus 1, which is k plus 2. So it's k plus 1 plus 1, which is really just k plus 2 all over 2. So this is what we must show. We must show that this statement, the left side equals the right side. So this is the way all these proofs go. You're going to use the inductive hypothesis. You're going to do a substitution, and then you're going to simplify the left side, and eventually you will reach the right side. So this is what I mean. So the first k terms are these, but we know by the assumption that that is equal to k times k plus 1 over 2. So that's what we're going to do. We're going to substitute k plus 1 over 2, bring down the next term, which is k plus 1. Just bring down the k plus 1 term. Now we need to simplify this and show that it's equal to the right side. So what I would do is put a 1 underneath, get the common denominator, which is 2. So parentheses here, multiply top and bottom by 2. And so now we have a single fraction, distribute, now you have k squared plus k plus 2k plus 2. If you simplify that, that's k squared plus 3k plus 2 all over 2. Then if you factor, you're going to get k plus 1 plus 2. And what do you know? We got that to equal the right side. That's what we're trying to show. That's pretty much the end of the proof. Now you just have to say, thus, p sub k plus 1 is true. Hence, or therefore, p sub n is true for every positive integer n. So that's the way induction works. If you follow those steps, you'll pretty much get any problem. Let's try another one. Okay, this one I'm going to write on a different sheet because I got a feeling that I'm going to run out of space. So let me copy and paste onto a new page. Okay, so let's start the induction process. So we always start it off the same way. Let Pn be the statement. And then you just rewrite the statement all over again. Okay, so that's the statement that we're using. All right, now we must show P1 is true since, now let's show that. So on the left side, we're showing that P sub 1 means the first term. So that's just 2 on the left side. On the right side, you plug in 1 for n. So you get 1/2 times 1 times 5 times 1 minus 1. If you simplify that, that becomes 1/2 times 5 minus 1 is 4. And that's 2 is equal to 2, which is true. So we've shown that P sub 1 is true. Now we have to assume that P sub k is true for some arbitrary k. So assume P sub k is true. And so let's write out that statement. P sub k is the statement. So now you just replace the n with the k. Anywhere you see an n, you just replace it with the k. So we got 2 plus 7 plus 12 plus ... plus 5k minus 3 is equal to 1/2 k, parentheses 5k minus 1. All right, so now we need to show that P sub k plus 1 is true. We must show that P sub k plus 1 is true. So let's write out P sub k plus 1. So that's going to be 2 plus 7 plus 12 plus ... plus. Always write the k term first, and then we'll write the k plus 1 term. So this is a k term, 5k minus 3, and then the k plus 1 term, now you're going to replace the k with k plus 1 in parentheses. So now you're going to have 5k plus 1 minus 3. So notice that I replaced the k with k plus 1 in parentheses, and now we have to distribute, combine like terms. So if you do that, you're going to get, this all stays the same for now. You got the k term, and now you have the k plus 1 term, which is 5k plus 5, take away 3 is 5k plus 2. That's 5k plus 5, take away 3 is 2. All right, so let's let's use our induction hypothesis. Remember, this is the induction hypothesis here. We're going to use that and substitute for the first k terms because we're assuming that this is true. So here are the k terms, the first k terms. We're going to replace that with this. All right, so that's going to substitute there. So now we have 1/2 k, 5k minus 1. Bring down k plus 1 term. And now we have to simplify that. So let's once again put 1 underneath here. The LCD is 2, so we got to multiply top and bottom by 2, just like we did in the previous problem. And now we have our LCD of 2. Now we can go ahead and distribute. So if you distribute, you're going to get 5k squared minus k plus 10k plus 4. All right, combine like terms, you get 5k squared plus 9k plus 4. All right, and now if you factor that, you should get, I'm going to move the 1/2 out here. It's the same thing. You can either put the 2 in the denominator, or you can just write it as 1/2 as a coefficient. So now the factors are going to be 5k times k, and it looks like we're going to get, let's see, if we factor this, we should end up with, let's see, that's probably going to be a 4 over here and a 1 over here, and that's going to be 5k plus 4k, which is 9k. So plus, plus, and that's exactly what we needed to get, because if you substitute the k plus 1 into here, you're going to get 1/2 k plus 1, 5k plus 1 minus 1. So I'm just replacing the n's with k plus 1's, and then distribute, combine like terms, you should get 1/2 k plus 1, 5k. That's going to be 5 minus 1, which is 4. So as you can see, this is what we were trying to get on the right side, and sure enough, we did get that. So that concludes the proof. So now we can say that, thus, p sub k plus 1 is true. Hence, or therefore, p sub n is true for every positive integer n. All right, so that concludes the proof. Now, let's move on to the last problem. Here it is. I'm going to copy and paste once again because it takes up an entire sheet. Okay, so let's do this proof by induction once again. So let p sub n be the statement, and then we just rewrite the statement. 1 squared plus 2 squared plus 3 squared plus ... plus n squared equals n plus 1, 2n plus 1, all over 6. Okay, let's show that p sub 1 is true. P sub 1 is true, comma, since, so that means the first term on the left, which is 1 squared, and on the right side, you substitute 1 for n, so you'll get 1 times 1 plus 1 times 2 times 1 plus 1, all over 6. So on the left, you get 1. On the right, you get 1 times 2 times 3, over 6, 1 equals 1, which is true. All right. Assume P sub k is true. So we're assuming that this statement is true. 1 squared plus 2 squared plus 3 squared plus ... plus. So remember, we replace the n's with k's. Okay, so that's the induction hypothesis. That's the part that we're going to substitute in for the next step. All right, so we must show that P sub k plus 1 is true. So let's look at what P sub k plus 1 looks like. So we write out the first k terms, and then we're going to write the next term after that. So let's write the first k terms first. 1 squared plus 2 squared plus 3 squared plus ... plus k squared. Now we need to write the next term after that, which is the k plus 1 term, and that's going to be k plus 1 in parentheses to the second power is equal to, what we needed to equal to is you replace all the k's with k plus 1s. So let's do that. Replace the k's with k plus 1s. You get k plus 1, k plus 1 plus 1. There's your k plus 1 plus 1, which is k plus 2. So I'm going to simplify that now. And then 2 parentheses k plus 1 plus 1. So here's a 2 k plus 1 plus 1. Distribute, combine like terms. You're going to get 2k plus 2 plus 1 is 3. So this is going to be 2k plus 3 all over 6. So this is what we need to show. We need to show that the left side is equal to the right side. So for the left side, we're going to put this part in brackets. The first k terms go in brackets. That's what we've been doing all along. And we're going to substitute the induction hypothesis into that because we're assuming that this is equal to this. So that's going to go here. So let's write that out. So now we have k plus 1, 2k plus 1 all over 6. Bring down the k plus 1 term. Write it over 1 because we need to combine these two fractions. So our goal is to make the left side equal to that, the right side. So let's see if we can do that. All right, it looks like we are going to. So you could multiply top and bottom by 6 like we've been doing. Expand that out, but that's going to be a little bit longer. I'm going to show you a shortcut. Whenever you have a common factor, such as you do here, k plus 1, I recommend that you factor out the common factor. It's going to make your life a lot easier. So you don't need this after all. Let's take out the common factor, which is k plus 1. So if you factor it out, that disappears, and this becomes to the first power. So now we're going to have, I'll put this in brackets. Now you're going to have k, 2k plus 1 over 6 plus k plus 1, close bracket. So all I did was I took out the k plus 1, and I factored it out, and now I'm left with k, 2k plus 1 over 6 plus k plus 1. Now I can put this over 1, multiply top and bottom by 6 to combine those into one single fraction. So this is going to make our lives much easier. So we have k plus 1, and then in the bracket we're going to have distribute. You're going to have 2k squared plus k plus 6k plus 6 if you distribute all over 6. All right, combine like terms, k plus 1. I'm going to move the 1/6 to the outside since we don't really need that underneath. And that's going to be 2k squared plus 7k plus 6. And then the final step is to factor that. So let's factor that. So now 16k plus 1. If you factor that trinomial, you should get 2k, k, and you should get 3 and 2. Let's see if that gives us 7. Inner is 3, outer is 4. 4 plus 3 is 7. So sure enough, this is going to work. And I'm going to rewrite the 1/6 as denominator 6. Remember, that is the same thing, just so that it can match up with the right side. And as you can see, they are the same. So we have completed the proof. Our goal was to make this equal to that. We substituted the first k terms with the induction hypothesis. We factored out the common factor. We combined the two fractions. We came up with one single fraction. We factored that trinomial, and we got exactly what we needed. So now we end the proof by saying, thus, p sub k plus 1 is true. Hence, p sub n is true for every positive integer n. That concludes this section.